Good morning again. It is still Tuesday morning, but I decided to prepare an optional lecture. It is absolutely optional. It has a small amount of important elements, which I will repeat on Thursday. So you don't have to watch it, but it's easier for me to prepare a lecture. It might not be as long as usual, then renumerate all my files in the website. So today we will talk about fluids again, but not static fluids like in a lake, in a pool. Moving fluids that travel through pipes. You open a faucet and the water gets into a sink. Well, an actual fluid moving through pipes is a complicated matter, and we don't really know more than we know about it, actually. We're going to talk about a very specific, simplified model of a fluid, an ideal fluid. An ideal means, first of all, incompressible. If you have a certain amount of fluid and you push and push and push on it, the volume remains the same. You cannot compress it. Of course, it excludes all the gases, but even air could be treated as a model of incompressible fluid for simple problems. Also, there is no internal friction, and there is no internal rotation, no turbulence. It's a steady flow. So if you take a droplet of paint and put it in it and let it move, you'll see a steady trajectory. And if you place several droplets, they will all travel in parallel trajectories. Very simple parallel trajectories. That's it. But right now, the most important property of an ideal fluid is this: you cannot compress it. So the density is fixed no matter what, no matter how hard we try to compress it. What does it mean? It means that if the pipe changes its diameter, if it's getting narrower or wider, because, well, the pipe has no holes, we cannot add an extra mass, an extra volume of a fluid in the pipe. We cannot get it out. That means every second, through any part of a pipe, we should observe traveling exactly the same amount of it. Because, again, you cannot squeeze it. And that means that the speed of the travel should depend on the diameter of a size of a pipe. So if you have a wide area in the pipe, it should travel here slower than at the narrow area, because you have to, I'll say, push through exactly the same amount of it. So this rectangle represents a certain amount traveling here, well, let's say in a second. But now the same amount should travel at the narrow end again in a second. So if you decrease the diameter, decrease the area, you have to extend it, make it longer horizontally in the direction of the stream. That means it should travel faster at this location. But the total amount is the same. So if we measure or calculate the mass traveling per second here and the mass traveling per second here, we should get the same number. And this number has a name: the mass flow rate, the mass traveling per second. Mass equals density times volume, and the volume equals what? Well, the area times length. And length equals distance traveled, and distance traveled over time, That's speed. So this is how we can calculate the mass flow rate. But if density is the same, we can cancel density. It means the volume traveling every second at every cross section in a pipe also is the same. And this product, when density getting canceled, this product has to be the same along a pipe. The area of a pipe times speed, area times speed, anywhere. And it doesn't matter what is happening to the fluid. It travels higher and higher, lower and lower. Only diameter, only size of the area affects the speed. Area is wider, pipe is wider, the motion is slower. Well, of course, we could imagine that a certain portion of a fluid travels and then getting, let's say, higher and higher. In that case, of course, force of gravity is supposed to do work on it. And against what? Well, somewhere on the left or on the right, there is a pipe attached to a pump. And that pump exerts an extra pressure. That pump exerts the force. And that force makes the fluid move. And for each tiny portion of this fluid, we could apply the Newton's second law, net force equals mass times acceleration. So an ideal fluid could be treated as a combination of small, tiny particles, and we could apply to an ideal fluid the same reasoning we applied to this skier traveling up. There is a work done by gravity, and that work should change kinetic energy. To calculate kinetic energy of a fluid as a whole doesn't make sense. But we can imagine we have 1 cubic meter of it. 1 cubic meter travels faster and slower, kinetic energy changes, and the work done by gravity changes kinetic energy. And if we apply work kinetic energy theorem, this is what we have to say. Change in the kinetic energy of 1 cubic meter, that's what density is, has to be equal to the amount of work done by what? By the pump due to pressure on that cubic meter, and work done by gravity of that cubic meter. That's it. And if we rearrange these variables, we get an equation that has a name, Bernoulli's equation. These are two equations we can use to describe any ideal fluid. That was the first equation. It has a name, continuity equation. It's a kind of a law of conservation of amount of fluid traveling in a pipe. The amount remains the same. That is why at the wider places it should travel slower. And this is basically the law of conservation of mechanical energy. Gravitational potential energy plus kinetic energy, and this term comes from work done by a pump. This is basically force times 1 meter of distance times 1 square meter of area, and that's pressure. And this sum of these variables remains constant, conserved. The law of conservation of mechanical energy. Of course, these two laws are identical, but no one uses work kinetic energy theorem. Everybody uses continuity equation and Bernoulli's equation. Done with theory, nothing else to learn. Now let's have some fun. This part, starting from now, is not related to the exam. This is just for fun. This is a device invented many years ago, has a name Adventurometer. What you see here is, let me switch to camera. Shadows kind of make it. All right. What you see here is a pipe or tube, a metal, aluminum, and you see here it's wide, here it's narrow, here it's wide again, and I've got also two plastic tubes with green liquid, and here I have the air source. Strong, so I can attach a hose to this device, Adventurometer, and turn the air source on slowly, or it will shoot it. If cool, this level rises, and this stays the same. Why? Well, you can treat the air traveling through this pipe as an ideal fluid. It's a good model, so why not? And explain what's happening. All right, now we need to switch to, okay. Simple do. And I need to move my camera back. All right. So, what is happening? Well, clearly here, yes, here, at this point, we call it A, you got more pressure. It's like a plunger pushing down on the surface, but because water cannot be compressed, so the amount of move down should go up. That means here, the pressure from above is not as strong as at point A. PA, PB, this air pressure at point A must be stronger than the air pressure at point B. This is just common sense. And here we can see the air pressure at point C is the same as the air pressure at point D. So this pressure here and there from air push equally. Well, now we can apply the laws. Okay. This is, of course, okay, let's start from this part. The continuity equation says this. If the area is the same, speed must be the same. So speed at part C equals speed at part D. That's all continuity equation says. But now we can apply the Bernoulli's equation. Kinetic energy, potential energy, and pressure, all 1 cubic meter. For air at point C and D, what we know is speed is the same and density is the same. Well, of course, for the horizontal flow, potential energy doesn't matter, it's the same. So we can make a conclusion now that the pressure is the same. We have it proved. So, okay, I just did it. Proving this. Again, this is the area number 1, or area A. This is the area number 2, or area B. The area A clearly is larger, greater than the area B. What does it say about speed? The continuity equation says this product has to be equal to each other. So speed at point B should be equal to speed at point A times this ratio. But this ratio is greater than 1. So we get a number and we multiply by something greater than 1. That means the result is greater than the initial value. Speed at point B is higher, it travels faster. What does it do? Well, Bernoulli's equation says of course, again, for a horizontal motion, height doesn't matter. But now, if I want to calculate the pressure, let's say the pressure at point A, it has to be equal to the pressure at point B plus kinetic energy of 1 cubic meter at point B minus kinetic energy at point A. But this difference is positive because we take one large number squared and then subtract square of a smaller number. That makes this pressure PA greater than PB. That extra pressure pushes down stronger. That's why we saw one level goes down, one level goes up. What is pressure? Well, we'll talk about it later in great details, but basically pressure is the result of collision. Molecules collide with surface, exert some force on average, force over area pressure. So when molecules travel fast, they just simply make less number of collisions then the same molecules travel slowly. That's why when the fluid travels slow, it exerts a higher pressure, assuming, again, the same level. Well, 2 slides which tell us how to explain this experiment. Next experiment. And again, I need to switch to camera. Now I need to lower my camera to, I think that should be good enough. Now I need to mute again the screen because it is distracting. All right, so I've got a ball. I've got the air source. Of course, there is kind of nothing special about this situation. You have a force pushing up, so strong enough to compensate gravity. But this situation is strange, right? Why it doesn't fall? Well, turns out Bernoulli's equation explains this. This airflow travels differently above and below. Here it's easier, here it's harder to travel, more obstruction. So here it travels slower, and because it travels slower, it exerts more pressure. So high pressure pushes up, low pressure pushes down, but higher is stronger, actually strong enough to compensate gravity and pressure from above. So because of the difference between how airflow flows above and below, it hangs, it's suspended in air. Here, I've got a golf ball, heavy ball. Why didn't it fall? Well, again, this ball makes air shadow below it. So the airflow above is fast and below is slow. Lower speed, higher pressure. So the pressure actually from above is so strong that compensate the pressure from below is so strong that compensate the pressure from above and force of gravity. Well, and I've got an experiment similar to my first experiment, but much more convincing. This is my ball. This is the air source. Leaf blower. I was able to hold it at almost 45 degrees. Why? Again, because of the same reason. The speed of the airflow above the ball was very, very high, and the speed of the airflow below the ball was so low that the pressure from below was so strong, exerted so strong force, sufficient to keep it in the air. Are there any practical applications of this theory? Of course. That's why airplanes fly. The wind is like that ball, essentially. And the airflow below the wing has a low speed, so the air pressure is so strong enough to lift so heavy machinery and make it move. Well, this is another practical application, fountain. Let's have more fun. What do I need? I need again, first I want to switch to sheet. Now I need to lower it. Now I need to mute it. So many actions. Why? No one created one uniform control device. Because no one really cared about providing good remote lectures. If people cared, I mean, didn't say they cared, but they really cared, they would have been doing something about that. And maybe now they will. So, I want to steal a gasoline from a car of my neighbor. I never do that. It's a joke. I need to move this water from here to here. So first, I'm gonna place this end of the hose here. And now I'm gonna place this in the beaker, and what's gonna happen? Nothing gonna happen. Why would it happen? In order to make this liquid, fluid, water move, I have to make a pressure difference. Well, first I could suck the air out, the water would be moving, and then I would let it go. Also, I can try to do it differently. I can first fill this up completely, this hose completely with water. Python. And now, see, now it travels down. And of course, if I flip it, I make a fountain, tiny fountain. Why is it tiny? Well, theoretically, in an ideal situation with no friction, according to the law of conservation of energy, that water would have been shooting to the original initial level of water in its bucket. But of course, nothing is really ideal. There is some friction. So in reality, without an additional pumping, it never reaches the original height. But with the extra pumping, of course, it could go even higher. So this is a siphon. This is a fountain. And how does it work? I'm going to move the camera again. All right, finally, I think this is over forever, so I can dump this green water. I will have to request for me new food coloring. But for now, for this semester, I'm all set. Find the speed of water at point number 1. Of course, it doesn't stop immediately. Of course, it travels, and again, in the ideal situation, it will travel this tiny droplet of water that shot upward should stop at this level. Final velocity here will be equal to 0, and the initial velocity here is the one which is we have to calculate in this situation. And well, how do we do this? Free fall acceleration. 0, y final, and v final squared equals v initial squared plus 2a delta y. 0 equals v initial squared plus 2 times -10 because acceleration due to gravity points down times 30 centimeters, 0.3 of a meter. So v initial squared equals 6. All right. Well, how else could we do it? We can imagine that a tiny droplet of water, which begins its motion here, eventually travels down to this nozzle, to the pipe, and then it's being shot here. Okay. So how does water flow? We know water flows according to two equations. The continuity equation and the Bernoulli's equation. Now, the good thing about this experiment, because we have air above here, air and air here, when we have a surface open to atmosphere, the pressure is equal to atmospheric pressure. And so I already have numbers here. So this point is set to be point number 2, and this is point number 1. So atmospheric pressure, pressure atmospheric. Same, we can cross it out. Height is different, but again, if I choose my axis, y-axis, like I just did, number 1 height is 0. Number 2 height is equal to 0.3 meter. What was happening below this level does not matter. And finally, speed. Now we're kind of getting difficult because this is what we're looking for, speed number 1. But the speed number 2 is not known. So we're kind of forced into using the continuity equation. All right. What does it say? Well, it says speed number 2 should be equal to speed number 1 times this ratio. What is the area number 1? The area number 1 is the area of this tiny circle. What is the area number 2? The area number 2 is the area of this huge circle. So A2 is much greater than 1, which means this ratio is much less than number 1. It's practically 0. So even if I don't know this speed 1 I'm multiplying it by practically 0. That makes this speed number 2 is practically 0. So I can actually cross it out. It is because the area at the top is much wider. So comparing two speeds, the speed of the motion of water at the top surface is negligible. It's practically not moving. Of course, it's an approximation, but it's a good approximation. What do we have now left in this equation? This is equal to this. And now you can see you can solve for speed number 1 and you get exactly same result. Density getting canceled. Square root of 2 times 10 times 0.3 square root of 6 meters per second. So, of course, everything has to match, has to fit. And for this question, the answer is 2. No friction, no air friction, no internal friction, so energy must be conserved. Now, calculate the speed of the same water, but at a different point. Speed at point B. At first, we think, okay, it's lower, so stronger. But when we say stronger, lower, stronger, we mean pressure. Pressure, of course, depends on height in general. But the question is not about pressure. The question is about the speed, and the speed is related to other speeds and areas by the continuity equation. And if we have area remain the same area, as long as the area is the same, the speed remains the same. So speed number one, speed at point B, or speed inside this pipe at point E. Why not? It's the same speed because area remains constant. The only reason for the speed to change is change in the size of this pipe. That's why this speed was different, practically zero. But of course, we can also compare pressure. So pressure number one plus kinetic energies number one plus height. Well, this is potential energy number one should be equal to pressure at B plus kinetic at B plus potential at B. Speed is the same, the kinetic energy is the same, canceled out. What I can do, I can redraw my axis, set zero at the lowest point, that makes this zero, but my height number one now will be equal to this. How do I calculate it? I need geometry, right? So what do I need? I need from here to here 1 meter minus 30 centimeters plus 20 centimeters. So 1 meter minus 0.3 plus 0.2, 1.1 meters. And this is the atmospheric pressure. We know the atmospheric pressure is equal to 1 atmosphere, which is about 10 to the 5th pascals. So now we know everything, and hence the pressure B will be equal to 10 to the 5th pascals plus. And pascals means, of course, international system of units. So we have to use kilograms, everything in units. 1,000 for density of water, all about 10 for G, and 1.1 for height. That's it. So that's going to be 4 years, about 1.1 times 10 to the 4th pascals, something, right? That's an optional lecture, so I can make mistakes. You have to check. All right, this is the answer, and one more illustration. The last problem for this lecture. It involves everything. And again, this is not a part of the exam number 3. So you can just stop watching right now. So what's happening? A big horizontal pipe with a given diameter is on the ground. And then it is bent because we want to use it to fill up the tank. So there's a big tank. So now it's actually getting wider here. Now, the tricky part is this. if this end of a pipe would have been open to an atmosphere, we would have to set the pressure from here at point number 2 to be equal to atmospheric pressure. But that's not the case. The pressure number 1 is not atmospheric, 2 atmospheres, so 2 times 10 to the 5th pascals. And this pressure number 2, is also not atmospheric, 6 times 10 to the 3rd pascal. How could it happen? Well, the only reason for that is if this whole setup is sealed, the tank is maybe something toxic. So, of course, there's a pump right here. So nothing is escaping to an atmosphere. Everything is sealed up. So maybe it's not even the water. This fluid travels and then filling up the tank. All right, and the pipe becomes 20 meters up. That's all we know. All right. I'm going to redraw the picture to show the pipe. Everything else is irrelevant. Diameter number 1, diameter number 2. Pressure number 1, pressure number 2. Of course, there's a speed number 1, speed number 2, and the height. And 2 equations. The continuity equation, the Bernoulli's equation. And well, naturally, we set the origin to y-axis at lowest level. So this is 0. And what do we have? Well, we are told it's water, so density is 1,000 kilograms per cubic meter, but maybe some kind of toxic waste. So 1,000 over 2 times speed squared plus the pressure, 2 atmospheres, 2 times 10⁵ equals 1,000 over 2 times speed squared plus, well, now 1,000 times 10 times height, 20 meters, plus 3 kilopascals. That's the equation we need to solve. But it has 2 unknowns. We cannot solve one equation for 2 unknowns. Luckily, we have another equation. A1 times V1 equals A2 times V2. That's the equation number 1. And this is the equation number 2. Well, area, pi, diameter over 2 squared, pi, diameter over 2 squared. We can actually cancel pi, cancel 2. So we've got a second equation with the same unknowns. 2 equations, 2 unknowns. Well, what can we do? I would square this equation first to get, for example, V2 squared equals something. Plug it in here. Solve this equation for V1. Then plug it back in here, solve it for V2. And then we had another extra questions. For example, calculate the volume floor rate. What is that? By definition, it's the amount of cubic meters traveled per second, but algebraically we proved it equal to this product. So if you know speed, you just multiply by area, done. And how many kilograms travel per second? That's mass flow rate. You just take density and multiply by volume flow rate. Done. And I believe I got this calculation. So the optional lecture is over. Thank you.